Okay, this is a review session for the first midterm. Um, as I said earlier on in the semester, it's good to review the prior exams because they will bear some resemblance to what you'll see on these midterms, even though they're prosecuted in a slightly different way. So this year, our midterm test will be 8 to 8:30 on Monday, Wednesday, Friday mornings of week number 5. There's a practice exam online, so you should look at that and see exactly how they're submitted to make sure. I'll probably take that down before the uh, midterm so there's no confusion as to which the exams are that you go to. But the exams will be posted on Canvas. You'll be able to download the exam sheet and you'll have to submit the answers online. So Canvas is going to be the medium for submitting. Review the practice example and also the previous tests I think would be useful. And if on the time of the midterm there's a problem with your internet going down or who knows what can happen, send immediately your answers. Don't need the working, but just the answers so that someone gets them within 5 minutes, and that would be fine. We don't want everyone doing that because that defeats the object of submitting the exams the way that we're talking about. But I think if there is some kind of problem, then we can take care of it by that in the few cases that we have. So get it to us immediately. Timestamp it, screen capture, and send it very quickly. So the material covered in this section of the class are really the first 3 weeks plus the fourth Monday. So it covers fluid properties for the first week. It covers pressures at a point for the second week for gases and liquids. Fluid pressures on structures, which is really week 3. And then the final remainder is for accelerating fluids. So that's the material that's present, potentially present in this part of the class. Only on the test is there a subset of that. So for the scheduled test, so I make the case that it's the scheduled exam only, the 3 questions on 3 different days are the following categories. If anyone has to take a makeup exam, it's not delimited by those topics. And so it's much less controllable if you take a makeup exam. And so I'd encourage you all to fit in with the scheduled exam as possible. So as mentioned, Monday, Wednesday, Fridays, 8 to 8:30 instead of class in the 5th week, this will be. Monday's question would be viscosity and buoyancy. Wednesday's question are fluid pressures at a point, ideal gas law and buoyancy also. And then Friday is fluid pressures on structures from week 3 and also buoyancy. Buoyancy seems to apply in all of these. So there's lots of material online that you can look at. There are previous review sessions from prior years that you can see, and you can hold those up against the exams that were on those occasions, and you can see that I'm not trying to lead you astray. I'm actually trying to be helpful in this. So this review will just go through very quickly some concepts that are embodied in these questions, just as a refresher. But for a full review of these materials, you should go back online or use your notes to study for them. So the first topic is fluid properties. And so under that, I guess, of relevance to this exam is viscosity. And so you all definitely know Newton's law of viscosity. The idea is that you take a plate, you move it at some either shear stress or at some velocity in the x direction. You look at the velocity distribution across the plate relative to the y direction, which would be perpendicular to the direction of motion. And you can plot, for instance, the change in shear stress that occurs as a function of the change in velocity in the x direction and how it changes with respect to y. In other words, this gradient here. And Newtonian viscosity merely means the fact that this curve goes through the origin. It's given by Newton's law of viscosity, which links shear stress that you apply to a viscosity, a change in velocity in one direction relative to the perpendicular direction. And if you rearrange this, of course, you end up with a definition of viscosity on this plot as being equal to mu and 1. This is a Newtonian fluid. A thixotropic fluid would be one that has a finite shear stress attached to it. In other words, you have to overcome the shear stress before it will move. In other words, at this point here, the velocity is 0 in the x direction. And so this is the shear stress that needs to be overcome. Units of viscosity, of course, are Pascal seconds or newtons per meter squared seconds by definition. And this seems a little blunter than I'm used to using, so I'll actually change this and change this back. Okay. So fluid properties in terms of viscosity. Fluid pressures. Well, in terms of fluid pressures, we know that in the case where accelerations are 0, then we reduce our more complex system of equations down to the fact that the change in pressure with elevation is equal to minus unit weight. And we know that the change in pressures with respect to the x direction and with respect to the y direction are 0. And so if you go horizontally, there's no change in pressure. We know that with this expression here, we can use this either for a compressible fluid, which would be a gas, in which case the density is equal to pressure divided by gas constant for that gas and for temperature. We know that these have to be absolute temperatures and pressures. And we know that for a liquid, density is constant. It doesn't change as a function of pressure, or changes only marginally as a function of pressure. And this defines how we deal with the magnitudes of pressure change with elevation. And so we can use these relations to, in the simplest case, give us pressure as being equal to a pressure at a point plus an elevation change times a unit weight. And we just have to be careful in terms of the sign that we use in that as we go up or down in a fluid. And that really just relates to the fact that if we take a fluid, the pressure change as a function of elevation, this is negative z in our convention, then for a liquid, we'd expect it to behave like this. And for gas, we'd expect it to behave in a curved way, not constant. In other words, this magnitude of rate of change of, if this is pressure, then this is unit weight, and this is 1. This gradient of this curve is not constant in space. And so this would be for gas. And we have expressions that we developed for gas, and for liquid it's rather straightforward. We've used that a great deal. And so we have to be mindful of the expressions that we'd use to that. So we have them for defining behavior in the atmosphere, for instance, as we go up from here. And we know that if you go up into the atmosphere, then relative to absolute pressure, P absolute equals 0, is the asymptote of this atmospheric curve as we go up in elevation. So that's fluid pressures both at a point and how they vary in the column. So those rules that we apply, we also apply to manometry. I'm not sure you need those in this one, but you know that if you go up in elevation, you subtract pressures. If you go down in elevation, you add pressures. if you're in a gas, then you can take that unit weight as being 0 without too much problem. If you're in a vapor, then the pressure of that vapor has to be the vapor pressure of that substance. And we can work in either pressure system that we choose. And so we could work in absolute, or we could work in gauge, in which case absolute pressure 0 is here. I guess gauge pressure would be minus 100 kPa. Atmospheric pressure would be 100 kPa absolute, or 101, and this would be 0, and so forth. And so we just need to be mindful. If we work in one form of pressure, we should probably stay that way for the rest of the example. Week 3 material was pressures on structures, or really forces, I guess, the effect of pressures on structures. And I guess a few things to remember here. One is that for on plane surfaces, if we're working on a plane surface, then we can certainly define, and I'll draw this in perspective, a coordinate system that defines behavior, that might have a plane surface on it. That plane surface has to be in a plane. It has to intersect the surface of the fluid in this particular case, and that is taken as kind of the origin, x and y. Y can be inclined, but y equals 0 has to be on the surface of the fluid. And we're interested in figuring out, I guess, a number of things. One is magnitude of force. What we've called FR, the resultant. And so we get that by defining the centroid of the structure, which in this case would be here. For that centroid would have 2 appropriate coordinates. It would have a depth of the centroid. So in other words, where it intercepts this surface here, and we call that h sub c, the vertical depth of the centroid of that plate. And from that, the magnitude of the resultant force is equal to the unit weight of the fluid multiplied by the depth of the centroid multiplied by A. This represents the average pressure which is applied at this point, and multiplying that average pressure by A gives you the total force that acts on this plane, and it acts perpendicular to this plane, but it does not act at the centroid of the plane. It acts at the center of pressure. And so the center of pressure, if I draw this out here, acts at an in-plane location equal to what we've called y sub r. And in this case, that point would be here. The magnitude of the pressure, force which is acting, would be F sub r, which we've just calculated. It would act at this point, and this particular point of action, if we define it here, so 2 point of action, well, it acts at the center of pressure, C of P, which our code, I guess, is YR. And we can always calculate YR as being equal to the depth, the slope distance of the centroid below the surface, plus the second moment of area around the x-axis through the centroid, and the slope distance of the centroid divided by the area. And so you can think of this as comprising, this is YC, this term here, and this term here is equal to this. don't know what to call it, but that's exactly what it is. And so the point of action is always below the centroid and always within the plane, and is always perpendicular, acts perpendicular to that plane. And so if we know the magnitude of the force, which is from this, and we know the location where it acts, then we can usually use that to define some kind of behavior to represent the structure. So I guess this would be delta yc. This would be delta yc. So with that information, I guess, we could think about using both the magnitude of the force and its location to be able to figure out the failure mode, if you like, for structure. And even though we get the magnitude or the location where the point acts, potentially by taking moments around any point that we wish, and we can use that, for instance, I'm trying to think, if you looked at a gate, as we have done in class, certainly you can get the magnitudes of the forces that are acting on this merely by using the distributions of these. And so if you wanted to, you could find out, if you know the magnitude of the force due to the constant pressure distribution and the force due to the triangular distribution, you could, for instance, take lever arms around any point you wish to and be able to get resultant force and the location of YR from that. So for instance, you could choose any point you wish, and it could be here, and you could choose this length and this length here. And if you wanted to know the magnitudes of the resultant force and where that acts relative to that same point, then you can merely write the expression as taking moments. So the the prismatic distribution multiplied by L prismatic plus the triangular distribution multiplied by the lever arm has to be equal to the resultant force multiplied by the location of the resultant. So from these two here, this force and this force, we certainly know that the resultant is equal to the sum of those two. So we can always calculate that because we know what each of those are individually. And so the only thing that we don't know in this particular case is this lever arm. So we can always solve for the lever arm if we do that. So everything that I talked about so far has not really been in failure mode. You could choose to take those moments around any position you wanted to. But if you want to specifically examine whether this gate will open or not, for instance, then you have to take moments around the position that you think it's going to fail. And so the moments in this particular case, as we did in class, have to be taken relative to the pivot in this particular case. So in other words, you'd write your moment equation around this point, and to be able to solve, as we did in class, I guess, for the magnitude of the force that was here that we didn't actually know. So that's important if you're trying to determine whether a gate will open or do something of that kind. There are a variety of ways that we can solve for forces on structures. You might remember for solution. And so we've done things all of these different ways. We drew up at the top the way of calculating where the magnitude of the force is and where it acts by using this kind of approach just at the top of this page. So we've seen this already. Define the centroid within the plane. That allows us to calculate the force as area times unit weight times the depth of the centroid. And the location of action as being this location here. And I won't write that out again, but that gives you the slope distance from the surface to the point of action of that, which would be this point here, which would be where FR acts. And of course, YR is equal to the in-plane depth to the centroid plus the second moment of inertia divided by the area times the depth of the centroid. This is Y sub C, right? Shown here. We could also calculate the magnitudes just by drawing it in section, such as if you have an inclined plate and you know the magnitudes of the pressure at the top of the plate and how they change towards the bottom of the plate, then you can certainly divide this up into two prisms and allow yourself to solve for F prismatic and F triangular. Because we know exactly where these act, this triangular distribution acts 2/3 of the length along this portion here. And so if we know each of these forces from the depths of the top and the bottom of this plate and the location of action of these, we can use exactly this approach here to be able to figure out exactly what the resultant is and where it acts. And finally, on the same kind of geometry, if we have a system that looks like the same as this, an inclined plane, then we can also, if we wanted to, divide it up into a weight of water that acts down here, a distribution of pressure which acts on the top here, which is uniform, right? Because it's at a single horizontal depth. And, oops, it wouldn't be that, would it? It would have to be this. Acting on the side. And so you can always divide your problems up into a variety of different geometries to be able to solve them. So those represent the ways of being able to solve for forces on structures and whether they fail by taking them around some kind of failure mode. And I guess finally, the last topic is buoyancy. And so the idea for buoyancy is sometimes it's easier just to do it. You imagine a cubic balloon below the surface. We know that relative to the liquid surface, the pressure distribution would look like this. Pressure versus depth. We know that these would represent the pressures at each of these locations. And so by definition, the pressure acting on the top is less than the pressure acting on the bottom. These probably aren't quite to scale, but this pressure base and pressure top would be equal to each of these. And clearly those are out of balance. And so if you're solving anything to deal with this, this displaced volume of fluid is missing. If the displaced volume was not displaced and was there, then this weight here would exactly counter the mismatch in these two pressures. But if it's not there, then we have to account for it. And so it's just a mismatch from these behaviors. And so the buoyant force acting upwards is just equal to the unit weight of the fluid multiplied by the volume that's displaced, in other words, this amount. And the weight of this particular structure would be what's pulling it down. So if this has a particular weight, then acting downwards would be this. And so by balancing forces, these have to equal 0. And so if we know the density and the specific weight or the unit weight of the fluid which is displaced, then we can calculate a buoyant force and apply that into our calculations for the stability, if you like, of the structure. And that, I think, is it. I think we covered all the topics that we talked about. Whoops. And so do look over this. Do look over the appropriate portions in the notes and the videos and go through them just to make sure those ideas are cemented in your mind. It's a different exam this year in that you have 3 separate days to do it. So that may make it a bit more manageable in some respects, but the time is relatively short. So I think you have to get cracking straight from the get-go and to be able to get these out. Okay. Good luck. Use the facilities available to you. Ishtak should be available in his office hours. Jai's available. I'm available if you need to get hold of people to ask questions. But do rely on yourself to go through the material and get it in your mind. I know it's appealing, the fact that it's kind of open notes and open book, but don't rely on that, because you have to do these things quickly. And if you know the equations but don't know how to use them, then you're missing a clearly important part of the preparation for the test. Okay. Well, good luck, and again, be in contact if you need any help in this. Okay. Thanks very much.